welcome back. We have two more talks before lunch today. First, we'll hear from TD right now, and then we'll hear about Mesos afterwards from Benjamin Hunman. So TD is a third year grad student working with Jan and Scott in the AMP lab, and he's been the leader behind Spark Streaming, which is near real-time processing on top of Spark, or a new extension, and he will tell you more about that now.
Thanks, Andy. Okay. Oh, does this work? Oh.
Just one click on the tab. Which one?
Okay. Yep. Thanks, Andy. So this is a project that we three grad students, Mate, I, and HY, we started towards the end of 2011. And the motivation behind this project was quite simple. So we have been talking about big data stuff. And a lot of this big data stuff, there are important applications that receive and process big data as soon as possible on a near real-time fashion. For example, page view statistics, click streams on ads, intrusion detection, spam filtering on, let's say, a stream of tweets. So these sort of things require the results of the processing to be provided as soon as possible, as soon as the data is received by the system. And the problem, as the data increases, we need to scale these systems to a lot more nodes, possibly hundreds of nodes. And the problem in scaling these applications to hundreds of nodes are actually twofolds. One is fault tolerance. It's not just for faults, but as well as for stragglers. It is necessary that since there is a very hard time bound, about 1 to 10 seconds for these applications, that you need to provide the results within that bounded period of time. Any crashes or any straggler nodes present in the system needs to be resolved, and results need to be presented even despite there being crashes and stuff. So the system needs to be very agile in dealing with crashes and stragglers in order to provide results in a timely manner. And the second challenge is efficiency in terms of resources. When you're scaling to 100 nodes, you obviously need to be cost effective. But the problem is that current streaming frameworks do not meet both these goals together. They meet one or the other. And I'm going to explain why, but let me finish with what the desirable properties of such a framework is. There are two other properties that we would want a framework to have, is a simple programming model, and if possible, an integration, the possibility of integration with batch processing as well as ad hoc interactive query processing. So that would allow a single platform that can do all your data analytics from batch processing to live as well as for ad hoc interactive queries. So I'm going to talk about that later towards the end, but I think that is one of the most interesting ideas that we got out of this project, and that is really exciting, and I would like people giving us feedback on this particular aspect. Okay, let's talk about traditional current streaming systems and the problems with that. So traditional streaming systems follow a particular processing model, what we call the record at a time processing model, where each record is processed individually. And so whenever the system receives a particular record from some live stream, each node in the cluster that is processing the stream maintains some mutable state. Whenever a record is received, it processes that record, updates the mutable state, and forwards that the modified record to the next node in the cluster. Now, the challenge out here is how to make this mutable state fault tolerant. And typically, there are two ways that traditional streaming systems make this mutable state tolerant to faults. One method is replication, where there are two sets of nodes that are in parallel processing the same stream. So one is the primary set of nodes, and the other set of nodes acts as a standby. So whenever one of the node fails in the primary system, the standby system automatically takes over. So here, the recovery from faults is quite fast, because it doesn't take much time to switch over, but it incurs a 2x hardware cost because you need to maintain completely two different set of nodes completely. The alternative method that systems use is called upstream backup, where there is no replication, but each upstream node buffers the records until the downstream node has processed them completely. And whenever a particular downstream node fails, a new node is brought up to act in its place, and the buffer and the upstream node replays all the buffered records to the new downstream node, so that after replaying, the new downstream node has the same mutable state as the failed node had. Now, while this does not require 2x the hardware, but the recovery is slow because you have to replay all the records in exactly the same order to this one, the new downstream node. So you can see either it is not cheap or cost effective, or it is slow to recover. And neither of the systems actually handles straggler scenarios, which are quite possible in clusters of large sizes of hundreds of nodes. So we started with this observation that that instead of record at a time streaming models, let's look at batch processing models. They have a very clear and efficient fault tolerance strategy, which is basically you have some data, you are doing MapReduce jobs, for example, on this data. Each of this job is divided into very deterministic tasks. So whenever there is a straggler or one of the tasks has failed, you can respawn that task on a different node, and you can get back exactly the same results every time, no matter how many times you replicate the task or rerun the task. So now we thought that how about carrying out this model to the streaming side of stuff. And so the idea that we came up with is, let's express a streaming computation as a sequence of batch computations on very small batches of data. So imagine you want to process a stream of tweets. Now, instead of processing each tweet at a time, what we rather would like to do is divide the whole tweet stream into, let's say, 1 second batches. Collect all the tweets received in every second, treat that whole tweet as, let's say, a Hadoop file, and apply MapReduce on it. It's a very simple idea. And now, since we are doing these batch jobs, we automatically, deterministic batch jobs on 1 second batches, we automatically get the fault tolerant properties that batch computations have. And now the challenge is how to achieve a good end-to-end as low as end-to-end latency as possible by this process. And for that, it's important to understand that the end-to-end latency directly depends on the batch size. Lower the batch size, lower is the end-to-end latency. So if you want to process in 10-second batches, then you have to wait for the whole 10 seconds for the whole batch to be collected, and therefore you have to wait at least 10 seconds. But if you do 1 second batches, you have to wait only 1 second for the batch to be collected before you can start processing. So the challenge is to make this batch size as small as possible. That is one. And now the earlier mutable state that I was talking about is the data that needs to be kept across batches is now kept in memory, and the operations that produce this state data is expressed as deterministic stateful operations. Because it's deterministic, these state data is also becomes fault tolerant. So let me explain it with a more concrete example. So let's say you have a stream of an input stream coming in. The data that is received between time 0 and 1 through the first second is received by the cluster and converted into treated as an immutable data set. It is stored reliably by replicating this data that is received. And now once we have this whole batch of data, it is passed through the usual batch operations like map, reduce, and stuff. And what comes out is another immutable data set, which we know gets RDDs. And so it is stored in memory as an RDD. So and this is like the state data. Now, when the next batch arrives, this state data is combined with the input data and the batch operations are applied on it again to create the next version of the state data. So these continuous sequence of immutable data sets that is produced actually forms the stream. So you can see that the left side of GARDs form the input stream and the right side is actually the stream of state data. Now, since all of these transformations is modeled as RDDs, and as we have seen already that RDDs remember the whole the lineage of operations that led to it. Each RDD knows how to recreate the RDD whenever any of part of it has failed using the dependency graph. All of these data sets present here, the input data as well as the state data is by definition fault tolerant. Fault tolerant without full replication. That's a mistake. Without full replication. So because they're fault tolerant, and so whenever there is faults or straggler, recovering from that fault or straggler scenario becomes very easy because all the data can be recovered in parallel, just like batch operation. For example, if this node dies and the state data that was present on this node goes away, you can actually recreate that state data because they are RDDs in parallel on all the other nodes. So this results in the fact that recovery becomes very fast because it's being done in parallel without the full cost of doing replication on all the data. So this kind of what we feel is the holy grail of what we want to achieve in a streaming in this kind of system. So the question is how fast does this model can go? And so we built a prototype on Spark, and that is what we call the Spark streaming. We found that this prototype can actually process quite a bit of data. We scaled it to 100 nodes, which together can process 4 gigabytes of data per second, which translated to around 40 million records per second, which is about per node around 400,000 records per second, all with a total end-to-end latency of less than a second. Let's dig a deeper into the results. So if you look at the cluster throughput, so here are 2 workloads that we tried. There is a grep, which basically receives a list of words and greps through them for a particular keyword. And there are top keywords, the top keywords received in last 10 seconds. And you can see that depending on what latency requirements you have, you can get a higher or lower throughput. So if you want 1 second latency, there is you will get a slightly lower throughput that can be achieved using the system. If you want if you are okay with 2 second latency, you can get a slightly higher throughput. So there is a inherent throughput latency trade-off in the system. But the cool thing is that given with dividing into batches and you can achieve 1 or 2 second latencies, which is acceptable in a lot of applications that we have seen. So we also did a comparison with the other existing systems, in particular Storm and S4, and this is the same grep and top K word count that I showed earlier, and this is a comparison of how the performance varies with respect to the record size. So in Spark, since we are aggregating all the data into a single batch, the size of the individual record matters less. So here in the x-axis, you can see that we have varied the size of the individual record in a stream from 10,000 bytes to 100 bytes. And the performance of Spark is largely unaffected. Whereas in case of Storm, since it also follows the record at a time processing model, so there is a certain overhead on a per record basis. Now, as the record size decreases, the total number of records in the same the total number of records increases. Therefore, the overhead increases, and therefore the total throughput of the system actually reduces. We also tried with S4, and it was limited to So Storm was limited to around 10,000 records per second compared to our 400 byte records compared to 400,000 records per second that we achieved on each node. We also tried Apache S4, which was limited to much lower values, around 7,000. Other commercial systems which are not open source report around 100K records per second. So we are pretty much in the expected range of 100K, 400K records per second. Now, question is, how fast can this system recover from faults? And this is a timeline which shows the processing time of each 2-second batches of data. And you can see that here, somewhere here, we actually introduced a fault in one of the nodes. This is this is a word count done on a 10-node cluster. And somewhere here, we introduced a fault on the system by killing a particular node, and you can see that the time actually increased out here, but not so much. And so it actually recovered it took less than 1 second extra to recover, and throughout this red period, we could see the effect of the fault. But after that, it again comes down to the usual processing time level. And so you can see that this system can be very agile because of its parallel recovery, etc. It can be very agile in recovering from faults. We have similar results for stragglers as well that I omit in the interest of time. So now that we have shown that, that this system is indeed feasible in terms of achieving the required latency while having the fault-tolerant properties that we desire, let's look at the programming interface. And I want to show you how intuitive and easy to program on this platform. So similar to RDDs, what the abstraction that we have out here is called D-streams, which is discretized streams, and which is nothing but a sequence of RDDs. So the stream effectively, conceptually represents the stream of data, even though that it is divided into a sequence of RDDs. And the API of this D-stream is very similar to RDDs. It has the same map, filter, reduce, etc. that you have seen for RDDs. And again, similar to RDDs, D-streams can be either created from a data source, which in this case is a live streaming data from network, or it could be from hard disk as a sequence of newly generated files, or by transforming other D-streams. Let's take a look into a more detailed look into the operators. So again, just like RDDs, there are two sets of operations that we can do. One is transformations, which create new streams from existing streams. And these set of transformations already includes the existing RDD operations. Plus, we have introduced a new set of operations called the stateful operators, which I'm going to talk in detail very soon. Then there are output operators, which allow the data that has been transformed using the transformations to be sent out to the external world, either saving to external storage or printing to screen or whatever you want to do with it. So let's start with a very simple example. I imagine there is a stream of words that are coming in over the network from a particular URL, and I want to count the number of words received every second. And so here words, and so the first line is basically creating the input stream, which is words. These are both, and then calling count on that creates a new input stream called counts. And these are both the D streams. And the count is basically an example of a transformation that we are doing. And what essentially happens from the RDD's point of view is data received between time 0 to 1 is collected into an RDD, and for each time interval there is a set of RDDs that is created, and each depends on the other. This is the dependency graph of RDDs every second. Let's make it slightly more interesting by counting the frequency of each words. And so this is similar to the word count example that you have seen for Spark and RDDs. Here we have a map and a reduce by key, where the map maps it to w,1 pairs, and reduce by key reduces the counts to get the counts. And this is a Scala little function that you've already seen while now, and this is the RDD lineage. Again, this is how it is. So this is, and this is not exactly the pseudocode. This is actually the code that you can write. But let me show you the full code that you will have to write. This is the full code, and you can see similar to the Spark context in Spark programs. Here you create a Spark stream context. That's the first line. In the second line, you set the duration, the size of this batch, whether you want to process every 1 second or every 2 seconds. 1 second or 2 seconds. Then this is the set of commands that you saw earlier. And finally, this is frequency.print is an output operator that prints the final frequencies on the screen. So this is a very simple output operator. Now, when all this is run, to start the whole stream computation on the incoming stream, you actually have to do this ssc.run, which initiates the whole the stream computation. So as you can see, similar to RDD's Spark's lazy evaluation, this is also kind of lazy. On to a slightly more interesting example, and where I will introduce you to some of the new operators that we created. Suppose instead of the frequencies of words every second, you want to see the frequency of the words received last 1 minute. So what you can do is you can use the operator that called window, which essentially aggregates all the words, all the frequencies received, all the 1 second frequencies into a 60-second frequency. And to explain the details of this operator, this window is basically a sliding window. The size of the window is 60 seconds, and it moves every 1 second. So what this will produce is the frequencies. It will aggregate the frequencies of last 60 seconds every second. And then you're actually again doing reduce by key on them to again get the final aggregate frequencies. And what happens essentially is that all the 1 second frequencies are aggregated together to create the with the window operator to create the window and reduce to 60-second frequencies. This is happening every second. And we found that this is a very common operation that stream processing environments would like to do, aggregating by a window. And so we kind of did a simple API trick to merge both these commands into a single command. Nothing special about this, but it makes things slightly easier. But let me talk about an interesting optimization that we have done on top of this. So let's say these window operators can actually be implemented in an incremental fashion. So for example, the window operator that I showed is a very naive one where all the previous 1 second frequencies are added together to create the 60-second frequencies. Rather, a more optimized way of calculating the 60-second frequencies is take the previous 60-second frequency, add the new 1 second frequency that got introduced into the window, and subtract the previous 1 second frequency. This reduces the amount of computation that you need to do by significantly, but it also requires a constraint. Not all aggregation functions can be implemented in this manner because, as you can see, it requires inversion function, which in this case is a subtraction because you need to subtract the previous frequencies. So only aggregation functions that are invertible can be implemented in this way. But in the API, we have allowed such functions to be specified as well. As you can see here, we have given this allows a developer to provide both the aggregation function as well as the inverse aggregation function, which in this case is minus. So this is some of the syntactic sugar that we have allowed in the DStream API that allows a lot more control for the developer to optimize the stream processing. So there are other interesting stateful operators that I will not go into in the interest of time. This is just a small preview. Let me talk about some of the output operators. Besides the one that you saw, print, which prints to screen, there are other output operators like save, which basically takes the input stream and saves it to any HDFS compatible storage. Then there is for each RDD where each RDD in a D stream is, you can apply any Spark function on each RDD in a D stream. For example, if you want to take the frequencies and rather than print to screen, you want to save it to some custom database, you can do something like this. Here is the more exciting part that we are all more excited about, the possibility of integrating live, batch, and interactive query processing. Now, in this case, we can actually, what you can do is we can take any D stream and process and combine it with any historical data. For example, in this case, suppose you have the word count frequencies as live data, a live D stream, but you want to join it with one day old frequencies and compare both the results of how does the frequency change from results that we had seen 1 day ago. And you can do something like that by doing a join on the D stream with historical data that you have on disk. You could do that. Then you could even get a slice of the live stream by using the slice operator, by giving a time range that give me all the frequencies between 2100 and 2105. And then you can do some operations on it. So, and this you can do interactively. This gives us the potential of a promise of having one stack that can do all your data analytics, that can fulfill all your data analytic requirements. Because what you can do is you can write an algorithm only once, and then you can run it either interactively or in a batch processing on a lot of files or on a live data. So for example, let me explain a particular scenario. Let's say you want to find a particular error in a log file, because you have, and as we saw yesterday, you could actually open up a Spark shell and interactively figure out by filtering and splitting the lines in the log file, figure out how to identify a particular error pattern. Now, once you have figured out an algorithm to figure out that error pattern on a Spark shell, you could take the same algorithm and apply it on a larger data set, on a larger list of log files in a Spark program. And now if you have validated that this particular pattern or algorithm works on a larger data set of files, you can take exactly the same algorithm and apply it on a live stream of logs that is coming in. If you want to do, you want to figure out and identify those errors in real time. So this cuts the complexity of managing two different stacks, one for batch, one for live, and it allows you to do a lot of flexibility. Like you can query a live stream for current data and combine it with previous data, etc. You can do a lot of stuff. And we have talked in our biennial AmpLab retreats, we talked to a lot of industry folks about this, and the feedback that we got from them is actually very exciting. They really like the idea of having one integrated stack. And so what we tried this summer, in summer I actually interned in Conviva, and we tried to see whether this conceptual integration is actually feasible in practice or not. So Conviva also maintains two different stacks right now, one for the processing live data, as well as another for the processing generating historical reports. What we tried is we tried to take the historical report stack, which is on Hadoop, tried to run it on Spark and Spark streaming to see whether we can actually get the required latencies and run it really fast or not. And we actually found that it is feasible to have one stack that can do both historical as well as live data analysis with acceptable latency bounds. And so that actually gave us a good experience and a good insight on that this is actually indeed possible. It's not just a conceptual feasibility, it's actually practical. And so we would what we would love to from you is give us more interesting scenarios where you would like, you may have a similar scenario, and whether you would like to try out something like this or not, your requirements, whether you can, what sort of processing you would like to do. So talk to us, me, Matei. Yes.
This is great work. I'm really excited about streaming. One question I had was the use of window operators.
Yes.
And the composition of RDBs that have been constructed using window slices. If those window slices are constructed either using slightly different window parameters, how do you know that the composed stream is synchronizing the individual constituents?
So that's a very good question. So the question is whether if there are different streams with different windows defined on them, how do we know that whether we can compose those two streams together? So we actually, the API in itself checks whether the those windows are same and whether they can be composed together or not. So that is inbuilt within the API to actually do those checks. So the programmer cannot make a mistake over there. Yes.
Where do you put the old batches, the old RDBs? Memory or just discard them?
So the user has control to whether keep them in memory or save them to any HDFS compatible.
Different users have different windows.
What's the question?
Oh, so the question is, let me see whether I understood the question correctly. So different users have different streams and they would like to keep the streams separately either in memory or disk. Is that the question?
Yeah, for example, do I have to, put all the old batches, all the RDBs in memory, or I can still on disk?
No, so you can save it to disk and the system will automatically take care of whether if you want to refer to a particular old batch, the system will automatically take care of pulling it out of disk if it is not in memory, so that the system automatically takes care of.
So as a programmer, you have to control this, right?
Yes, so you have the hooks to control of where do you want to save it and how do you want to save it, but the system makes it seamless to actually combine old data that is from disk with new data and things like that. Yes.
Do you get some kind of notification if you're not keeping up with the input pipe?
That is a very good question. So the question is whether the system gives any kind of notification whether the system can not keep up with the input stream or not. So right now it doesn't, but this is an ongoing research project, so we are actually considering doing something like this and figuring out what is the right batch size and dynamically changing the batch size as the inputs load changes. So we are actually actively thinking about this, and so we will probably have an answer sometime soon, but not yet. Yes.
Can multiple users interact with the same stream to do different processing simultaneously?
So right now, no. So right now, since this is all built on Spark, Spark does not have Spark does not have the inherent capability to share RDDs across the process boundaries, but we have research projects going on to enable that. And Jan briefly spoke about it when we have this project called T-Rex, which allows RDDs to be saved onto an external process in memory, and then that process allows the RDDs to be shared from multiple different frameworks. And with that thing in place, then different users can run different Spark streaming programs and share the same RDDs. So it's not in place there yet, but this is something that is in our pipeline. Yes.
My question is pretty simple. How do I supply the input data? Is it like files on HDFS? Does it automatically pick up the stream from the input data? How do I supply the input?
So there are multiple ways you can specify an input stream, either from a network or from an HDFS. You can give it a directory, and whatever new files that is getting generated in that directory will be automatically picked up by the system. So there are multiple ways you can introduce new data into the system, and we actively encourage people to actually implement their own input stream formats, because the input dstream API is very simple, it is very easy to override it and create your own sources of streams. Yes.
It seems like one of the major difference in terms of workflow is that in Spark, I write a job, submit it, and then something comes back. This is obviously running indefinitely.
Yes.
So one of the things that Storm does very nicely, once I submit my topology, it keeps it running. It doesn't matter if something goes down, it just runs. So I was wondering what this new framework would do in that case.
So the question is, Storm, for example, keeps the processing pipeline running given if a particular node dies or something, and whether Spark streaming can do the same or not. And the simple answer is yes. It is, since it's built on Spark, it inherits the same fault-tolerant characteristics as Spark does. So whenever any node goes down, since all of this is all the data is expressed as RDDs, the same fault-tolerant characteristic will kick in, and the RDD will be recreated.
If the node that kicks the whole thing off goes down, that was mine.
Okay. So you're talking about the driver program.
Correct.
And in Spark right now, there is just one master driver program, and as it is now, if the master dies, yes, the system dies. We have been thinking about making a distributed master using Zookeeper that make the master tolerant to faults as well, but it's not there yet. So it is a very valid question right now. Cool. Yes.
Just to verify, I think I know the answer. Just to verify.
Sure.
You say that the processing does not depend on the size of the message this much. So this is why you provide your input characteristics in gigabits per second or whatever that
Yes.
thing. But from point of view of where data is ingested, is it ingested in one place, or it can be ingested in parallel multiple places and then processed in the stream?
It can be ingested in parallel or multiple places. In fact, the results that I showed, there are 100 streams being ingested in parallel on 100 nodes.
And you would have those 40 gigabyte per second. Would it be across all of those, or it would be per node?
So per node, it was across all of those. So on each node, it was 40 megabytes per second.
Okay.
So each node was receiving 40 megabytes per second of data and processing it.
Okay. Thank you.
Okay. Anything else? Okay, let me move on. So to implement this on Spark, we actually had to do a lot of internal modifications in Spark, because Spark in the current 0.5 version cannot do tasks as fast as we'd have liked to do. So we optimized a lot of the scheduling in Spark to do sub 100 millisecond tasks. We also implemented a distributed key value store that can store blocks of data and move around blocks of data using very fast GNIO data transfers. Also, to pipeline jobs from different time intervals, we allowed pipelining of jobs. And so these changes to Spark are already available in the dev branch, but the streaming platform is not yet. But we hope to release an alpha version of the streaming platform soon with Spark 0.6. If you want to know more details about the abstractions or the Spark streaming, the whole idea of Spark streaming, you can refer to our paper. That is the URL. Thank you.
Thanks, TD. We're going to take questions offline for this one to move along to the next talk.